Okay, so let's begin with this one. This is an interesting one because it's tricky to graph. You could get a little confused in either way, but let's just start off. So here's my function, uh, x plus sine x. And I'm going to draw a set of axes here to sketch it onto. And I really begin by trying to imagine what this looks like. And it might be good practice to just see if you can come up with a few rules about this function before you even begin. The first thing that I realized was that this piece over here is bounded between -1 and 1. It doesn't matter what x is, it's always going to be that this whole thing is between -1 and 1. And x isn't bounded, right? X could go off to negative or positive infinity, right? In either way. So what I realized was that, for high values of x, this is going to be very high. And then for very negative values of x, this is going to be very low. So I had some intuition in that regard. But beyond that, I wasn't too sure what this function looked like. So after that, my intuition was done. So I just started doing the calculus. I said, okay, let's take the derivative. And it's a simple derivative to compute. But something interesting happens when we set it equal to 0. We see that there's actually infinitely many solutions to this equation. So I set it equal to 0, and I move the 1 over to the other side. I get cosine x equals -1. And if we look at the unit circle, right, when is it that cosine x is -1? It's -1 over here. And that means that it's -1 when it's pi, but then you could go around again for 3 pi, 5 pi, 7 pi. So you get this, and you could go -1 pi, -3 pi, right? So what you get is when you draw this, your real line with where your derivative is 0, you get a range of values. You get pi, you're going to get 3 pi, you're going to get, actually I'm going to make it so they're closer together because there's no reason not to. 3 pi, 5 pi, 3 pi, 5 pi, of course, 5 pi, and so forth, 7 pi. And all of these values will make this derivative equal 0, or this derivative equal 0. And you could sit here and negative pi, -3 pi. And that's actually key because what happens when the derivative is 0 is that the slope of the tangent line is 0. So the curve, what this function, is flattening out at each one of these points. At pi, at 3 pi, at 5 pi, at 7 pi, so forth and so forth. You want to see what's happening in between on these intervals, right, that you've divided. So this interval here, right, this interval here, this interval here, this interval here, so forth and so forth. You want to find out what's happening on these intervals. So you just pick a point in each one of these intervals. 0 is here. So let's see what's happening at 0. And when I plug in 0, cosine of 0 is 1. So I'm going to get a positive. 1 plus 1 is 2, so it's positive. So my function is increasing from negative pi to pi. Let's see what's happening from -3 pi to negative pi. So if I plug in -2 pi, right, -2 pi, if I go along the unit circle, I go, that's negative pi. -2 pi is back here, and I get 1 again. So 1 plus 1 is 2, and my function is increasing on this interval as well. And once I had this information, it sort of enabled me to graph it, because then I said, okay, well, I'm going to mark off these key points, and I had an idea of what this function looks like given what I started with. So I'm going to maybe plug in pi, right? When I plug in pi, what do I get? Well, -1 plus 1, I get 0, right? Is that right? Pi, -1. Oh, no. Plug in pi into the original function. Sorry, I'm like, yep. Okay, pi plus sine pi, right? Because I know that the slope of the tangent line is 0 at that point. right here at pi. So let's see what's happening here. It's going to be sine of pi. Sine of pi is 0, so I just get pi out. So let's say that this is pi up here, pi right here. And then I can plug in like 3 pi. Let's see, that's 1 pi, 2 pi, 3 pi. I'm going to get 0 again. I'm going to get 0 again. And then, yeah, and then it'll be 3 pi up. So it'll be 3 pi up here. Exactly. And it's flattening out at these points. What's happening at 0? 0 is a nice one. It's 0. Okay. And negative pi, you could check, right? Negative pi, sine of negative pi is 0 as well. So it's negative pi over here, this point right here. And you get this progression here. And it looks like it might be in a straight line, actually, but it's not, which is also pretty interesting. This function is, in general, pretty interesting, especially trying to graph it. And you can maybe see, is it negative? Yeah, because for all of these values, right, negative 5 pi, negative 3 pi, negative pi, sine is 0 for all of those values, right? Negative pi is 0, right? The y value for that point is 0. Negative 3 pi, you know, so forth and so forth. You keep going. But basically, yeah, you're going to get 0, so it's just going to be these x values. So it's going to look linear along here, which is cool. But you get, if you don't want to sketch the curve yet, I have an idea of what the curve looks like. But you want to get more information, of course, let's just take the second derivative. And you get negative sine x. And now you set the second derivative equal to 0. And it's whenever sine is 0. So let's mark off where that's going to be, right? So let's pick blue and let's say, so let's see, where is it that sine is 0? Sine is 0 at 0, at pi, at 2 pi, at 3 pi, at 4 pi. Okay, so sine is 0 here, here, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, so forth. And then negative pi, negative 2 pi, negative 3 pi, negative 4 pi, and so forth and so forth. And now you have where it is that the second derivative is 0. Now, each one of these points are actually going to be an inflection point. So I'm just going to make this a little bit bigger. I'm going to draw another line so it's not all overlapping. 0, and let's say pi, 2 pi, 3 pi, negative pi, negative 2 pi, negative 3 pi. And then I pick points in between these intervals. So these are all the points where the second derivative is 0, these ticks. And it broke it up into infinitely many intervals. You pick any point in between. So let's try, I don't know, negative pi over 2. Negative pi over 2 is right here. Sine is negative 1. So then that means that it's concave down all on this interval. And then let's try pi over 2, right? That's between 0 and pi. If I plug in pi over 2, that's positive 1. So it's concave up here. And it flips back and forth. So like 3 pi over 2 is between pi and 2 pi. 3 pi over 2 is, this is pi over 2. This is 2 pi over 2. This is 3 pi over 2. It's negative 1. So it's down here. Oh, but the original derivative is negative. So everything flipped over the other way. But that's okay. Okay. So since it's negative, I just changed the sign the wrong way because I forgot that this is negative sign we're talking about. Where negative sine is 0 is the same place where sine is 0. So then everything flips. So if it were, so I plugged in negative pi over 2. What happens to sine at negative pi over 2? It's negative 1, but then this is negative negative, so then this is plus. And it's concave up here. And then at pi over 2, it's going to flip. And it's just going to go back and forth. You could test and you could check with test points that it looks like this. It goes back and forth, concave up, concave down, concave up, concave down. And now with this information, we kind of have to be in a position to sketch it. So we want to know that it flattens out at each one of these points. These points I got originally from the first derivative. So it flattens out at each one of these points, but it also inflects at each one of those points. So what your curve looks like is that it looks something like this here. Okay, where it does this like stepping kind of thing. And it inflects also right at this point right here. It inflects at this point, but it also inflects here. So if I make this graph a little bit bigger, so let's make it bigger so maybe we can see the behavior a little bit more zoomed in. So let's say this is pi. Let's say that this is 2 pi. And then let's say that this is 3 pi over here, right? And then I sort of have my sketch. So what does it look like? It flattens out at pi. It flattens out at 2 pi. And it flattens out, oh no, it doesn't flatten out at 2 pi, it just inflects at 2 pi. And then it flattens out at 3 pi. So what does it look like? It looks like this. And it inflects at that 2 pi, it inflects at 3 pi. And then this is sort of like what your general curve is going to look like. You should see that there's inflection points. Look, it inflects at pi, it inflects at 0, it inflects at 2 pi, and it inflects at 3 pi. Look, the tangent lines right here is like overlapping. It's not above or below at 0, but then when it goes above, right, this is concave down, concave down, concave down, and then it overlaps, and then it's concave up because the tangent line is below, and then it overlaps, and then it's above, which means it's concave down, and then it overlaps. It's not concave up or down, and then it's beneath the line, so that means it's concave up, and it goes back and forth forever, sort of like what it looks like right here. This is a very interesting function overall, if you ask me. The way it sort of steps and the way it even progresses linearly like that, like on the intervals of pi is interesting. And then like it has that nice curvature and how it goes back and forth between being concave up and concave down. But nonetheless, it's always non-decreasing. Anyways, okay, let's do the next one. The next one is also fairly difficult to graph, especially if we don't have a good intuition for this. So let's go through this next one. So the next one is x times e to the negative x. This is the function we're asked to sketch. And I had no intuition for this. I rewrote it a little bit. I said x over e to the x. And I realized what was happening at the end behavior. So I tend to look at the end behavior, right? So in the beginning of the last problem, I looked at the end behaviors, right? I looked at what's happening when x is very negative, and I looked at what was happening when x was very positive. When x is very negative here, the result is very negative. Okay, you should convince yourself. Look, if x is like negative 100, then it's negative 100 over e to negative 100. But then this e to the negative 100 comes up and multiplies. And then this is positive times a negative, which makes it very negative. And e to the 100 is a very negative number. So I realized that fact. And then I thought, what happens when x is very positive? When x is very positive, it's tricky. Like, let's take 1,000, right? We need to know that this is tending towards 0. Because 1,000 over e to the 1,000, this bottom piece, the bottom piece is going to grow way faster than the top. So the limit as x goes to positive infinity of x over e to the x equals 0. So we have that horizontal asymptote now going off only in the positive x direction. Once I had that, the fact that it's very negative when x is very negative and that it's close to 0 when x is very positive, after that I didn't have any other intuition of what was happening in between here. So again, I relied on calculus. I said, okay, let me take the derivative of this. I took the derivative using product rule here and chain rule, but here I'll just do quotient rule on this one, same thing. So f prime of x is equal to the derivative of the top times the bottom minus the derivative of the bottom times the top, and then the bottom squared. This could be simplified a little bit, and you want to do that. This could be written as e to the x, 1 minus x over e to the 2x, and then this cancels with one of those on the bottom, and you get a nice simplified version of 1 minus x over e to the x. And now you have your derivative. You set your derivative equal to 0. 1 minus x over e to the x equals 0. This is 0 only when x equals 1. And you draw out the number line. And you divide your line into just basically two pieces. Everything to the left of 1 and everything to the right of 1. To the left of 1, let's say 0. 0 gives you a positive, which means that the function is increasing all the way to this 1 value. So let's say 1 is right here. If 1 is right here, right, you want to plug into the original function. 1 over e to the 1. 1 over e to the 1 is just 1 over e. Let's say 1 over e is up here. That's a point that you want to mark off. Now, what's happening when x is greater than 1? Well, when x is greater than 1, you get 1 minus 2, which is negative. This is still positive. So your function is decreasing. So that means that it comes from way down here. We said that it's negative. It reaches some max, this point 1, and then it begins to decrease. Now, how it decreases and how you want to handle that, I would definitely not start to sketch it until I then computed the second derivative and saw what's happening with its concavity, because concavity gives it away. So take the derivative of this. The derivative of the top is negative 1 times the bottom minus the derivative of the bottom times the top, 1 minus x over the bottom squared to 2x. And then this you could simplify as, what is it? Negative e to the x. Wow, hitting everything. Negative e to the x minus e to the x plus x e to the x. Is that right? And then once you have that, so wait, what do I do here? Okay. E to the x. Right, e to the x. What's going on? Oh, I hit the eraser. That's why. Okay. E to the x like that over e to the 2x. This becomes negative 2 e to the x plus x e to the x. And again, I could factor out an e to the x and cancel. So I'm going to get negative 2 plus x over e to the x as the second derivative. And again, this second derivative, this equals 0 if and only if x equals 2 in this case. So when x is 2, this whole thing equals 0. Now, with that in mind, what you can do is graph out this here. So let's say 2 is over here. I don't know. Okay, whatever, 0 is here. It divides the interval into, again, two pieces. And you want to see what's happening with concavity for everything to the left of 2. So take like 1. 1 is a good test point. 1, negative. This is positive. So then it's concave down all here to the left of 2. And then 3 is going to make it positive. It's concave up. And 2 is an inflection point because it changed its direction. So what that means is that if 2 is like somewhere over here, it's nice because you can see that, look, it's concave down all here, right? The tangent lines are all below the curve, all here. So let's forget about this over here. Oh, wow. Okay. Let's forget about all of that, right? And then now let's go back. And yeah, let's just draw it again. If you look, right, the tangent lines, they're all above the curve, which means that it's concave down. All here, it's concave down until eventually at 2, it flips, and then it goes and it flattens out to get to that horizontal asymptote where the tangent lines are now below the curve, and it's concave up after 2, which is what this is saying over here. And this is more or less what the sketch looks like. It does have its max at 1 over e, and yeah, I mean, this kind of gives it away, the calculus aspect, because I didn't know what it looks like. But the second derivative was very helpful in that, you can kind of see how it inflects at that one point there. But either way, both of these functions are difficult because they require a decent amount of practice and intuition about what these functions look like. I would say again that you should start off thinking about what the end behavior is of this and in the other one, right? What was the end behavior of this? I realized that this was increasing for x and decreasing going down the other way. That's useful because, you have to have that match with your calculus now. You could reference it back and forth, but okay, either way.